this computer. Perfect. I'm going to share my screen. All right. Can you guys see my screen right here?
Yes.
Yeah, perfect. All right. Well, we're going to go ahead and do some quick review. Hold on. Here we go. We're going to do some quick review on what we covered yesterday. So the main points we're trying to look at is stereochemistry. So the first thing is alkene stereochemistry. So for alkenes, whenever you have a double bond in a compound and you're naming it, you have to put E or Z. And how I remember it is with the alphabet. So right here, C is at the beginning of the alphabet, and so is Z. So C and Z are paired. And on the inner side, you have E and T, E and trans. That's how I remember it. If you have your own way, I don't want to mess it up. Whatever you like to remember, use that way. If you want to use this one, feel free. It's just what I know. Secondly, is also using the alphabet for our alkyne reactions with a triple bond, 2 pi bonds. So boration, or your reaction with BH3 is usually going to be BH3. If not, it's going to be R2, BH. Just any kind of BH and then bonded to two other things. THF, for the second step, H2O, hydrogen peroxide, and then H, I think it's NaOH. That gives you an aldehyde. A and B, very beginning. And right here toward the middle, you have ketone from mercuration. Mercuration being H2O, H2SO4, HgSO4. All right, that's what they prefer to be. So if you have a mercuration reaction and you have a internal versus terminal carbon for your alkynes, mercuration will prefer the internal one. And the opposite for boration, if you have an internal versus a terminal, boration will prefer the terminal. And if both are internal, and it's going to be mercuration, most likely, you have 2 products because both internal ones can be ketones. Additionally, when we're naming stuff, don't forget our priority list. We have 3 main priority groups. Alkene and alkyne are kind of in the same spot. So that's why we like to group them together, but alcohol is at the very top. So if you have an alcohol in a cyclic compound, that carbon already becomes carbon number 1. If it's in a just normal non-ring compound, you have to go whatever branch gives that alcohol the lowest number. If alcohol is not present, then amine groups become the priority group. If that's not present, then whatever alkene or alkyne group you have. And they work as a pair, as in whatever combination gives both of them the lowest numbers possible, without regard of any halogen or alkyl groups you have, just as long as the alkene and the alkyne get the lowest numbers. If it's a tiebreaker both ways, the alkene gets priority. But I doubt you'll encounter that. But if you do, just prefer alkenes. And then lastly, this last group, just halogens like Cl, F, then ethers like methoxide or ethoxide, and then alkyl groups like methyl ethyl groups that are at the very bottom. They're not priority groups at all. And that's not to be confused with R and S stereochemistry, which we'll get to later. But when we're looking at R and S stereochemistry, we're not looking at this kind of priority. We're looking at atomic weight, right? Line we want to make sure we have. Let's move on to our review on the alkene reactions. We're going to go over the mechanism just a little bit, but these are the main 3 you have to know: halohydrogenation, halogenation, hydration, and then solvation. All right. And all 3 of these are Markovnikov addition. All 3 have a carbocation intermediate, hence Markovnikov. But because it has a carbocation intermediate, hopefully that rings something in your head. That means that it can shift. So you have to already look at the alkene, you have to label them. We have tertiary, secondary. Which one is the carbocation going to be in the intermediate? Someone want to just yell it out or type it in chat.
You would want the carbocation on the tertiary carbon, right?
Yeah. So if we got rid of that alkene, obviously break that up, you have the H here, the carbocation right here, right? It's already on a tertiary carbon, so no shift is necessary. Even though it could shift, if there was a possible shift, it won't, because tertiary is the carbocation ideal. If it was something like this, right? This is a secondary, this is secondary, and this right here is a quaternary, and it has a methyl group to share. So if the carbocation was right here, it could trade places with that and become a tertiary, which is something it would ideally do. But again, if it's already on a tertiary on carbon, doesn't really need to do anything. But that's how the shifting works, is mainly with the three mechanisms you need to know step by step. And if we were to write out, all right, let's bring back our reagent and just write out the products. As we know, this is the tertiary one. So this is Markovnikov right here. So the Br, or whatever halogen you have, the nucleophile. So the most electronegative atom. So if you had Cl and I, Cl would be the most electronegative. So that would be your nucleophile. Then your least electronegative, or the H, which usually is on that non-substituted alkene head. And H2O is pretty much the same thing, where you split up that water between an H and an OH. Basically, that's not how the mechanism works, but that's how I just split it up. H, and then the OH, or the H2O, and then it's deprotonated, but you guys get it. The OH would attach again to that carbocation. And then for the solvation, it's the exact same thing, but instead of an H, we have an alkyl group, like methane, or a methyl group, and then H, it's the same thing. And these right here, they're the same mechanism. So you kind of only really need to memorize two types of things, because they both use sulfuric acid as a acid catalyst. Moving on to stereochemistry. Remember, clockwise is R. So if you go clockwise, it's R. Counterclockwise is S. And I always remember it. This is something I posted in the chat as well. You know, the direction I write it in, you know, this way. That's how I remember it. Yeah. And this is only true if the fourth priority group is dashed. That means it's in the back. A very common error I found last night when I was grading the problem sets was this problem right here, where, all right, we have, obviously Br is going to be our first priority, and hydrogen is going to be our fourth priority, because hydrogen is the smallest atomic mass element there is. So there's nothing really smaller than that. So it's always going to be 4. And if you have 2 hydrogens, it's not a stereocenter, because for a stereocenter, all 4 bonds have to be unique. And now we have to assign 2 and 3. Well, the way we do that, since C's are the exact same atomic mass, we look at their bonds. This C is double bonded to another C, so it counts as 2 C's, 1 for each bond. Then that 1 H. This C has 2 H's because that's CH2, and is bonded to 1 carbon, or that methylene group. So 1 C. You have 2 C's versus that second C, or against that third C. And that's where you have to look at the extra layer of atomic weight if there is a tie. So obviously this one would be 2, and this would be 3. All right. Now, you might be thinking, all right, 1, 2, 3, that's clockwise, we want to do R. However, if you remember what I said, it's only true if the fourth priority group is dashed. However, it's not dashed, it's wedged. And whenever that is the case, whenever, there's only one thing you have to do, switch that to S. Because if you pancake flip it and turn it to dashed, then you reverse the entire thing and it's S. So that's what the answer was for that problem set question. And that brings me to the case of our Fisher structures. So right here, we have, remember, the horizontal lines are wedges, and whatever vertical line we have are dashed, right? So if you have H on a wedge right here, whatever stereocenter you get right here has to be reversed. So let's say this was an OH, for example, okay? So our first priority group would be bromine. I don't know why I wrote G. First priority group. Our second priority group would be the carbon right here attached to the oxygen, 2, and then the methyl group would be 3. So that would be 2, 3, that would be S. However, because that H is wedged, we have to change that S into an R. And that same logic applies to here, where if you have H already on a dashed, whatever R and S you decide is there is already correct. All right, that's something really weird that you should keep an eye out for, because H is on this horizontal line for Fisher structures can be tricky. There's not a whole lot of application other than just like knowing it's there, because for the problem set, you guys didn't have to do that at all. You kind of just looked at the BRs and the OHs because this is, again, relative conformations, but something good to know. All right, so when you're applying them, don't forget to reverse it. All right, so if we, oh yeah, this goes into the rules of Fisher structures and just a lot of the structures you'll deal with. And this also applies to structures where you have just like a cyclohexane and then like wedged, dashed, and wedged groups ends up. But in order to maintain stereochemistry in the plane it's sitting on, you cannot pancake flip it side to side or up and down. You have to rotate it in that same plane. That's all you can do. All right. So for this one, if we were to rotate it 180 degrees, this is what we could get. OH, Cl, H, H. And hopefully you guys can see what I did. I just rotated it around. That's completely correct. It's still the same molecule because it's in this normal plane and its conductivity is the same. And if let's go ahead and assign SS or SR, whatever we have here. All right. So right here, we would have 1. This would be 2. This right here would be 3. And our H is on that dashed line. So we can just circle it normally. That's going to be clockwise is going to be R. All right. Now let's look at this atom, not atom, this carbon. All right. Br is going to be 1. Cl is going to be 2. This carbon right here is going to be 3 because it's attached to Br. And then again, our H is in that 4th group. So we can just count it normally. That's 1, 2. That's going to be counterclockwise or S. If we rotate it around, right? Let's look at this. Br1, Cl2, this 3. H is in the dash, so we don't have to flip any kind of counting. That's going to be S. Hold on. Okay. And this is going to be R. Whoops. All right. So we have for this group right here, the BROHs, that's still R. And then for the BRCL, that is still S. So SR going to SR. All right, by our rules, they're identical, they're the same. That's the kind of logic you want to go with. And that's going to help me pivot to this next point. When you're trying to decide if it's diastereomer and enantiomer are identical, basically the entire bottom portion of your problem set, what I like to do is just write out your R and S situations. And then whatever you're comparing it with, you write that one too. So if your initial one, like let's say, if you're thinking about your problem set, if it was SS, If you had SR, that'd be a diastereomer. Because there's only one difference in it. If there's two or more stereocenters, but there's one difference in stereocenter, then it's a diastereomer. There's only one or more differences. If it's a complete reversal, RR, it's an enantiomer. Because there's a complete reversal. And this goes into the idea of a mirror image. If it's a mirror image, then all of the entire compound has to be reversed. And then again, if you have the exact same SS, no change at all, afterwards, it's identical. You have to make sure you look out because the branches always have to be the same. Because if you're looking at, let's say it was a product D, for example, and they did a switcheroo on you and made that BR into an F, you got to watch out for that. That would be different. But I doubt he would throw that at you, but just be diligent on what you're comparing. But does anyone have any questions on what we've gone over so far? This is just like a quick review on what we talked about Tuesday. Any questions, voice them now. Anything you want me to go over again? Or if this clears a couple things up. Great. Do you guys want me to move on, or do you guys need a minute to write things down? If you want, I can also like post this on the group me.
Yeah, can you put this on the group me, please?
You have to hold me accountable for it. And in the chance I don't do it, make sure you message me and then I will. Thankfully, you guys had the entire weekend, but just hold me up to it. All right. We did this on Tuesday, but we're going to do it over again just because we need to know how important, you know the steps of these mechanisms. So for this one, we have solvation. Now for the solvation mechanism, there's kind of two parts because we have to perform a separate reaction creating the oxonium ion. The oxonium ion is basically that ion where we have a positive charge on that oxygen, because that will create a Bronsted-Lowry acid. It just makes that OH group a protic group, and they can just transfer things to other compounds. So for creating that, our alcohol CH3, CH3OH. And then for the structure of H2SO4, you will have to know the structure of sulfuric acid. I know that might be AS, but you have to know it for the mechanism. So this oxygen has two lone pairs. It'll snatch up one of those hydrogens. And this is the one step you have, CH3, CH2. Oh, that's supposed to be 2. O, H, H. Don't forget, whenever you draw mechanisms, you have to draw every single lone pair and make sure you have formal charges. It's super important because the point of the mechanism is to show that you know what's happening. Then you have your residual counter ion. All right. And this is all you have to do. This right here is our oxonium ion, the big money maker. What you have basically. Yeah. I think in semester 2, test 3, we had to know a couple of mechanisms, probably ranging from 6 steps to, we didn't have to know it, but there was one mechanism we did in class that was like 10 steps, formation of an amide from a carboxylic acid. It's a lot of fun. Okay, let's get on with our alkene. So right here, I'm just gonna notate it. That's what our alkene looks like. Just want to check. 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. Okay. So if we have our acid right here, H, right? That double bond opens up, grabs that hydrogen, that bond goes. One sec.
If you, or you on the phone?
Give me 1 sec, yeah. Zoom recording. Okay, can you guys see my screen still?
Yeah, we can still, I can still see it.
That's all I need. I got a thumbs up from Julie as well. The lone pair would go there. And again, rate determining step. That's something you do have to write out. Make sure you write rate determining step. It's super important because it's always the formation, pretty much always, 9 times out of 10, the formation of the carbocation. Because I think some lab techniques would be like, all right, how do you speed up or help alleviate the rate determining step? And you might be like, I don't know, add excess alcohol, stuff like that. Formation of carbocation, and then right here, I'm just gonna write that H as it is. And then again, you have a byproduct of that alcohol once again. Right? And now there's a nucleophilic attack. The lone pair attacks there. Then we have H, O, H. Don't forget when the nucleophile attacks, oxygen has 3 bonds and there is a positive formal charge. And then you have, this is a neat step where you can write another alcohol, because an alcohol is a perfectly good base, but I just like writing B lone pair because any convenient base is present. So for this one, because it could either be another alcohol or it could be the counter ion of the sulfuric acid. Not likely, but valid. Valid. We're not picky. This is just basic OChem. Any base would just pick that up. Then you would have, oops, the H there, O, and then the lone pair. And then you're welcome to do the HS4 minus, and then whatever convenient base you have there. Honestly, you can, if you end up using alcohol, you're welcome to just write stuff like that. Anyone have any questions on this mechanism? I'm going to take the silence as a yes. And now this is the fun part, alkyne nomenclature. This is really interesting because, again, when it comes to nomenclature, alkynes and alkenes have the same priority, disregarding any kind of tiebreaker. So for this one, let's go ahead and count our carbons. This first one, 1, 2, 3, 4, 5, as a pentane. Pentane, we'll get there. And we have an alkyne and a BR. An alkyne is a priority group, BR is not. So we have to number it 2, 3, 4, 5, use it the lowest number. So if bromines are 5, 5 bromo, pent 2, ine. Set. It's pretty easy. Now we have an enine, an alkene, and an alkyne. And this should be something that rings something in your head. Whenever you have an alkene that's not cyclic and is a stereocenter, you have to do E or Z. All right. For test 2, when I was in OChem 1, what I did was, all right, I made mental checks. When I was redoing all those practice tests, I always made sure, okay, at the very end, did I put E's and Z's where necessary? Did I put R's and S's where necessary? That's all I did. And I think one of the tests, it did save me. I'm like, oh, I forgot the E and the Z. And the thing to note right here, this alkyne is not a stereocenter. You don't have to do E or Z because again, that only happens when your things have different groups. Hold on. When they have different groups. So if this is R1, R2, R3, R4, if they're all different, then yeah, stereocenters. However, if you had R1, R1, R4, R3, if they're the same, like it is here, not a stereocenter. Right? Yeah. And that means on the same side, because even if like we know that these are H's, right? If they're H's, they're on different sides. So E and Z does matter because both sides have different, groups. But with that being said, let's go ahead and just name this. Well, I just said that this is an E or Z conformation. Does someone want to spit out if it's E or Z? Or in the chat. The chat doesn't hurt. You only just type one letter in the chat. I'll read it. I'll be like, oh my gosh, you're right.
Would it be trans,
Yes, it would be trans.
which is the E?
Mhm.
Okay.
What is going on with my Zoom? I need my menu. There it is. Okay. Okay, I'm good. It would be. And there's only one of these alkenes, so you just have to plop that E right there. Boom, you're done. That's the very beginning of the entire thing. Don't worry about it anymore. All right. Now let's count both ways. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So we have 3 and 6 versus 2 and 4. Which is the best one? Obviously 2 and 4. The methyl group, that's just a branch. So we'll have 6 methyl. That's 1, 2, 3, 4, 6, 7. Hept 4 ene 2 ine. Yeah. Anyone have any questions regarding that? I don't think so. All right. Now let's look at this other E9. All right, both ways. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We have a 1 and a 4 versus a 1 and a 4. Here's a tiebreaker. Which one would take priority? The alkene. So we know that we want to go this top route. So it's going to be a pent, what is it? Pent 1 ene 4 ine. Let's go ahead and slap that 3 fluoro on there. And we're done. No E or Z, because again, this one is not a stereocenter. There's 2 H's there. So stereochemistry doesn't really matter because if you were to hypothetically rotate it, which you can't, there's no difference. Another situation where you don't have to apply E or Z conformation to an alkene is that it's cyclic, because cyclic compounds, this might sound stupid, but are kind of cis. They're cis. The only time you'll have a trans alkene in a cyclic compound is if the cyclic compound gets to the size of like 16 or 18 carbons plus. That is where it's big enough where there's no steric strain of the hydrogens, playing to each other, but don't worry about that. Right. So this is cyclohexane, let's cyclohexene. However, we have a priority group, OH. The moment there's a priority group, OH or amine, that takes priority over alkene. That's the first carbon. All right. And now we have to number it. One, if we went this way, 2, 3, 4, 5, 6. The other way, 2, 3, 4, 5, 6. We want to number this outer way so we can give that alkene the low number. You would get 5 bromo.
How did you run your even trash?
Uh,
You're gonna be grass?
yeah. I'll replace the liner. Five bromo. You too. I don't need that dash. Cyclo. Hex 3 E 1. Oh, you know. Right. That was pretty straightforward. It doesn't throw any like anything weird at you. Does anyone have any questions regarding the names we've gone over thus far? Because these are pretty complicated. They're doozies. A common thing for both of them is this alkenes. Alkenes. So you need stereochemistry. Alkenes, you need stereochemistry. For this one, let's just go and get these out of the way. What is it, E or Z? So interesting, is it cis or trans? It says. So C, beginning of the alphabet, end of the alphabet, Z, have Z. So our very beginning is Z. And we just leave that B. Right here we have an E. And we have a Z. Is the O and then the C. Yeah. An Z. And we'll take care of those later. So if we were to number them, well, okay, alcohol is there, so it has to get the lowest number priority. It feels this way: it's 1, 2, 3, 4, 5. So just this way: 1, 2, 3, 4. 4 has to be the number we use. It's going to be 4 all. So we're going to use numbering starting from this left side. So 1, 2, 3, 4, 5, 6, 7, 8. And this is where we will apply our alkene. So if our alkene bridgehead that we started is at 4 and it's Z, 4, Z. And then our second one is E, and it starts at the sixth one, 6, E. That's all we have to do. And now we can just number it normally. This is an octane, right? Octa, 4 and 6. Diene. And then all is always like the most, or all is going to be your suffix. So it's E9 all. 2 ine. Make sure you drop that E for all. All right. Is that good with everyone?
Can you over why it's the 4Z and 6E again?
4Z and 6Z. Whenever you number the alkyne, or not the alkynes, the alkenes, it's always that first carbon you're coming across and you're in the direction you're numbering it that you apply the C or Z to right here. And then you cross the bridge. That's your alkene, but it's always that first carbon that you're trying to apply that notation in. Because if you have 2 alkenes, well, at each of these carbons, 4 and 6, what's the stereochemistry for them? Well, at 4, we have Z, and at 6, we have E.
So like on the second one we did, if we put 4E, would that be incorrect?
4, we would accept it.
Okay. But it's okay if you just have one to just use the number or the letter like E or Z as we've been doing.
What's up?
So if it's just like the second one, it's okay to just use the letter like we've been doing.
Yeah, you're welcome to use 4E. That's in my book, that's still correct, because if you're right, you're not wrong. That's something that Dr. Berg says. So that's all good. That answer your question?
Yes, thank you.
Cool. All right, this last one. See? All right, we have an alcohol and an amine. What is the priority group in this one? It's going to be the alcohol. 1, 2, 3, 4, 6, 8, 9. Some people might stop here, but we have to keep going. 10. Now, the alcohol is on the 4th carbon. I kind of already know that that's going to be the way we go, because if we went the other direction, pretty sure the OH would be on like what, the 6th or 7th carbon. Not not what we want. We want alcohol to have the lowest number. So I know it's 4. It's going to be 4 all, and we can just number it the way we go through it. So Z, like what you said, we can do 2Z if you want. 2Z, 6 amino. It's the first one. Amino's done. We have a dimethyl and then a third one. That's a trimethyl. We have 5 di substituted. 5 di substituted, and then another one at the 9. Trimethyl. I'm going to do ... here. There's no space or dash. Trimethyl, we got rid of this, and now we have the alkyne, the alkene, and the OH. So we can go ahead and stick in our parent name, deca. I think. Deca, okay. Alkene first, 2, ene, 7, ine, and then 4, all. All right. Yeah, that's it. I thought there was more. Okay. So pretty big doozy of a naming question. Fear not, I'm 99.9% sure he won't throw something this crazy at you. This is just to show you different techniques on, again, trying to mix the priority list with alkenes and alkynes, and more practice on what order you name them. And if you have all 3 groups, if you're putting them in the suffixes, the alkene first, then the alkyne, then the alcohol. Does anyone have any questions? We already did reactions of alkynes. All right. And now we're going to get into stereochemistry. So we did the nomenclature. We're about to get into this, and that's pretty much it. So why don't we go ahead and take 5 minutes, take a quick stretch break. I don't want to over fry the rest. Just chill out. You guys are doing good. I'm going to recording. Perfect. All right, it is recording. Let's get into RNS. All right, R S. And this first part is really straightforward. We just assign R and S. Did I skip a section? I did, didn't I? No, wait, we already did that. I am a dummy. What am I doing? Chirality. I did skip a section. Okay, I thought I was tripping. Okay. This is the first part of your problem set. And you have to circle which ones are achiral. Well, by definition, the achiral means it has an internal line of symmetry, right? For this one, a lot of people might think, well, you have one group that's BR, that's not a CL, there's no internal line of symmetry. Well, all it needs is one internal line of symmetry. That could be right down here, and it would be achiral, because if you flip this that way, it's mirrored, right? It's mirrored, it's the same compound, or same side. So this is achiral, it's symmetrical. That would be the same case. And yes, you can do that for BR, even though that's a BR, it's symmetrical, because it's on that line of symmetry. So if you had something like this, BR, CH3, then like CL, take those wedges too. This would be achiral. There is an internal line of symmetry straight down. All right. And these wedges kind of really matter if they're not on the line of symmetry, because they're the ones actually folding. But the stereochemistry here, even though if this BR is dashed, it's on that line of symmetry. So we can just draw it right through it. It doesn't really matter. It's the beauty of the tetrahedral atoms. All right. Now, we have a Newman projection. Just go ahead. I'm going to highlight this and save me some room. Nope. Achiral. Newman projection, you just rotate it so that things match up. So for this one, it's really easy. Just rotate it 60 degrees. So if you did, when you eclipse it, which is again what you want in eclipse formation, OH, CH3, H, let's rotate that eclipse formation for that front carbon, OH, however, H and CH3, this matches up, but these do not. If they don't match up, it's not achiral, it's chiral. Let's move on to this one. This one's really easy. You're looking for a horizontal line of symmetry. Boom. This side is the same as this side across that line of symmetry. Same thing with CH3 and CH3 here. And this beyond that H don't really matter because it is that line of symmetry. So it's there. The line of symmetry is right there, right down the middle horizontally. And again, you can write it on the atoms. So right here, it is achiral. For this one, we have another Newman projection. And what do we want to do with that? Well, we want to rotate it so that they match up. So let's rotate this 180 degrees over here. It's supposed to be bond angle. Let's rotate the CH3 180 degrees over here. Bond angle of 180. If we did that, our Newman projection would be, let's do CL, CL, CH3, CH3, H, H. Well, look at that. CL's match up, CH3's match up, H's match up. It is achiral. All of it matches up. So we can highlight that. This is achiral. Now for this one. All right. Well, we have a cyclohexene. If we were to cut it across here, that's not symmetrical. BR is not the same as CL. If this was BR, yes, it would be symmetrical, but it's not. Let's do it vertically. If you had a line of symmetry right here, it's not symmetrical because you have the alkene here. However, if the alkene was gone, let's say it was just a right here a cyclohexane, and that was your molecule, it would be achiral because the line of symmetry is just straight down the middle. So that would work. But alas, it's not. All right. Let's move on to absolute configurations, R and S. And something to remember is that R and S only apply to tetrahedral atoms. So if you see a dashed and a wedged, it's a pretty big indicator that you have R and S. Remember, alkenes right here. Alkenes don't have R and S. It's not tetrahedral. There's not four bonds. There's 3 bonds. So you only have to look at the top-down view of the plane, and we get either Z, cis or trans. However, tetrahedrals again do not have cis and trans. They have R and S. With that in mind, let's just start from the beginning. Okay. Cool. All right. So if we were to look at this top left one, we're just going to go straight down on this left side. This is 1. This CH2 Cl would be 2. Because if you see here, there's carbon, carbon, carbon. We have to look at the next layer of connectivity. And for this one is connected to a Cl, so that's the next heaviest. And for this one, there's a carbon-carbon bond. So this is the 3rd heaviest. And this would be 4, the 4th heaviest. And this right here says, all right, our 4th group is not on the dashed plane. So let's number this normally, 1 to 2 to 3. That would be 1, 2, 3. That would be S. Oh, wait, it's on the wedge. Yeah, that would be S. Because if I have my model, because if you're looking at it just from the side, that 4th group would be away from you. I don't have my model kit on me, but if you guys did, you guys would be able to see it. The model kit with the 4 group away from you, you would still be looking at that direction. 1 to 2, 3. So that would still be S. Yeah, okay. For this one, we have edges right here, dash right here, right? CLs are priority group for number 1, CH2BRs are number 2, and then CH, our geminal methyl group, I don't know why I wrote 2, will be our third group. Our methyl group would be 4. You can see that the fourth group is already dashed, so we can just count it normally. This is going to be 1 to 2, 3. It's going to be S. Normal counterclockwise. This one's a little harder. So these are stereocenter. Let's look at the carbons. Well, okay. Carbon, 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 carbon. Let's look at the second layer of connections. So this carbon has 3 carbon bonds. This one has 2 carbon bonds. This one has 1 carbon bond, H, H. And this one has 2 carbon bonds, C, C, H. So I know that this methine group is our first one. This one is our fourth group right here. And now we have to look, okay, we have CCH and CCH. They're tied. You have to look at the next layer of atomic weights. It's kind of ass, I know. But thankfully, the next layer, tiebreaker, is right here, BR. So this would be our second priority group, and this would be our third. Great. All right, now let's look at it. 1, 2, 3. That's going to be counterclockwise, would be S, but our fourth group is not dashed, it's wedged. So we have to flip it around. So that would be R. All right here, another Fisher structure. We have 1, 2, 3, 4. These ones are pretty given. BR is the heaviest, hydrogen is the least heavy. This one, you have a carbon-carbon tie, but this one right here is connected to another carbon, so it would get priority. So it would be 1 to 2 to 3. This would be R. However, H is on a wedged line, so you have to reverse it. If H is on the wedge line, or the fourth priority group is on a wedge line, reverse it to S. That's it. This one, all right. H is wedged. Let's keep that in mind. Same thing with this one. H is wedge. So BR1. This one would be 2. That carbon would be 2 because connected to BR, even though this carbon is connected to oxygen. If you're looking at that second layer, oxygen is lighter than bromine. This would obviously be 4. So if you're counting this 2, 3, that would be S. However, hydrogen is on that fourth priority group. So you have to reverse it to R. Let's take it from the top. We have 1, 2, 3, 4. Yep. 2, 3. That's going to be R. Hydrogen's on that wedge, so we have to change it to S. Let's get this last one. All right. OH. 1, obviously. Hydrogen. 4, obviously. Now we have an ethene group and an ethyl group. Well, this has a carbon-carbon bond. This CHH bond. So this is heavier. This is going to be 2, 3. 1 to 2 to 3. That's R. And hydrogen, the fourth group, is dashed. So that checks out. Is that good with everyone?
Can you explain the first one we did again? I'm having issues like conceptualizing it.
Sure.
Thank you.
So for the first one, well, we know our numbers are right. 1, 2, 3, 4. If you're looking at it from here, right, you're counting it normally this way, because if this was, let's say this is our conical view, If we were to redraw it, CH3 would be back there. BR be here. CH2CH3, CH2Cl. That's what we would see if we were looking at it as a cone this way. Our fourth priority group is not on a wedge. It's not on a wedge, so we don't have to reverse it.
Okay, thank you.
Cool. All right, let's go ahead and move on. This is an interesting one. Now we take the rules of our stereochemistry. So right here, let's go ahead and assign R and S, our absolute conformation. We know, all right, 1, 2, well, hydrogen is always going to be 4. 2, because carbon's attached to Br, and there's going to be 3. That's going to be S. For this one, we have 1, 2, 3. This is going to be S. However, H is on a wedge, so we have to reverse it. R. S versus R, they're enantiomers. There's a complete reversal of all the stereochemistry, and there is because it's only one letter. Now for this one. All right, well, this one's really easy. Remember, stereochemistry, or the stereocenter 1, stereocenter 2, only has 3 bonds, so it can only be E or Z. So this is E. For this one, this is Z because they're cis, right? This one's really easy. Cis versus trans, well, they're diastereomers. Because if they're enantiomers or a mirror image, they would still be trans. Because imagine if you held a trans, here, a cis, this is better, a cis molecule up in a mirror. Well, if the mirrors are looking at each other, it's still cis in that mirror. However, if there's only one difference, if it's a trans, that one difference makes it diastereomer. Does that make sense? Okay, I hope that makes sense. And if it doesn't, memorize the fact, and yeah, hopefully you won't encounter it. For this one, remember, you cannot pancake flip it. All right, you can only rotate it. So if you were to rotate this, you would have, hold on. There we go. If we rotated it, we would have CH3, CH3, CH3. And you see how it's the exact opposite of the wedge formations there. If all 3 stereocenters are different, or the complete reversal of their enantiomers, we know that. Right? However, cool thing to note, if this was dashed for any kind of reason, if it was dashed, there's only one or more differences, it would be a diastereomer. But it's not. Why does it say that? What? Do you guys see this where it says January 9th? That's weird. All right. Okay. Right here.
Also, it's not Tuesday.
I know. I'm like, wait,
And
I
it's
looked at it,
not-
I'm like,
it's
not
also not 9
9:41
a.m..
Yeah, I was about to say, like, it is not. When the iPad tries to gaslight you. Okay.
Guys, we've got like 6 months until the test. We got this.
If only.
Oh yeah. All right. For this one, okay, you remember that alkenes have E and Z stereochemistry. You can pancake flip that. I know it goes against pretty much everything you or I just told you, but alkenes, they're all on the same plane. You can pancake flip it because for a tetrahedral atom, all right, those are all single bonds, they're sigma bonds, so they can rotate around an axis. So like if you had carbon, let's say you had like a big compound and your stereocenter had this carbon right here, like OH, Br, Cl. This sigma bond can rotate around. So stereochemistry is really important. However, pi bonds, they cannot rotate. And they only have 3 bonds or 3 electron groups. So we only have to do cis or trans. And that's the thing. If they're not rotating, well, we can pancake flip it. We can pancake flip it. So that's super easy. So if you have an alkene, well, you literally just pancake flip this over and they're the same. That's a cool rule. Or not cool, tough. But hey, that's okay. All right, final column. So we have right here, this is a chapter 1, not chapter 1, test 1 concept. We have axial, axial. Well, if we do a chair flip, equatorial, equatorial, that makes sense. They're the same. If it was equatorial axial, they're obviously different, but these are on different planes. For chair conformations, my biggest tip is just drawing it as a cyclohexane. So if this was axial CH3, this would be dashed. That's what it looked like. And this still applies here. But it's kind of easy. If it's a chair conformation, every axial will change to equatorial and vice versa. And if they're the same compound, then yeah. The thing that he would trip you up on that is, what if he made this the axial? They have to be on the same kind of carbons. So if it was here, let's ignore this. That'd be 1,3 dimethyl versus a 1,2 dimethyl. And thus they would be constitutional isomers. All right, keep an eye out for that one. And let's go ahead and use our rotation rule, because look at our tops and bottoms, they're kind of different. So what I like to do, I just like to rotate it so that they are on the same plane. So let's rotate this over. CH2, CH3 here. CH3 is now on the top. Both of these H's go on this side. OH would go here. Br rotate all the way to this top portion. All right, so it would be Br and OH. And you might be thinking, all right, well, if you look at this, it looks like the RNS are different, but the connectivity is different. The Br is on this methyl terminal. However, on this one, the Br is on the ethyl terminal. Something you can't really catch straight up, but if you look at it and you're trying to figure out if it's RNS, hopefully that's when it'll come up like, oh, they're different connectivity. So these are different, or not different, constitutional isomers. This one, really easy. If you look at it, all right, methyl group, methyl group, methyl group, methyl group, hydrogen, hydrogen, Br, Cl, they're different. Straight up. Last one, all right, well, again, if you have a cyclohexane with branches, I just rotate it. Rotate because it keeps in the plane of the paper. CH3, CH3. Okay, now let's look at the branches. The carbon connectivity is right, dashed, wedged. However, there is one stereochemistry difference. If there's one, I'm not going to take the time to write it out. Let's say this was RS, RS, R. This would be S. be RSR versus RSS. There's only one difference, that's diastereomer. That's it. Does anyone have any last minute questions?
Can you post this in an announcement on Canvas?
An announcement?
Yeah,
Yeah.
I haven't been able to join the group me because I don't know my password from high school.
Don't worry. Don't worry about it. Do you have access to the YouTube videos?
I don't know. I haven't been able to find them.
All right. I'll post the recordings for the review sessions as well, because Tuesday's review session, in my opinion, covered a good amount of the important tips and tricks for this test. And if you ever want to watch more videos for the office hours, because I posted the one for the office hours yesterday, just click the channel and there should be some helpful resources there. Yeah. But I'll make sure to post all this on the announcement. Same thing with these notes up here. If you weren't able to get them, or if you weren't here at the beginning, these will be available. All right. Does anyone have any questions?
So now that we actually have some time, I'm gonna be doing the practice sets you gave us. Is it all right if I email those to you tomorrow and I can get like,
Yeah, email them
All right.
whenever and I'll
Yeah.
take a look at them.
awesome, thank you.
Same thing with the test. If you guys haven't done the test I posted now, if you don't have ready, just email them to me and I can grade them manually. Just like check off which ones are right and wrong.
Now that I actually have time, my plan is to just go through all the different things tomorrow.
Yeah,
It's like studying.
yeah. I'm gonna stop my share now. Nope, never mind. There we go. I'm gonna go ahead and stop the recording.